Just to start, I think it's really important to understand what is ophthalmology because I think it's a field that is not as studied as other fields like histopathology or X-rays, like radiology overall. But it is a field that has a lot of relevance for the body and also for the social implications that can have like some ophthalmological problem. So first of all, we should understand that many of the problems that we have in our body actually are reflected in the retina. So not only visual problems, but also problems like diabetes, cardiovascular problems. There are many papers showing that you can actually see the progression and see inside of those other clinical problems just from the retina. So this is one thing. It's a really powerful clinical indicator, but also there is another thing that is really important, and is if you have an eye problem, let's say blindness, something like that, this is also affecting a lot the patient in a social way regarding the way how the patient will interact with the world, the way how the patient will do their own things, and even psychologically. So there are some studies showing that the patients have a worse self-esteem if they have ophthalmological problems. So regarding that, we have a lot of medical imaging modalities that we can use to see the retina, and this is actually something quite amazing because these are not invasive methods. Like we can just use these machines like tabletop cameras to take pictures of the fundus of the retina, or we can take OCTs as a way to scan your retina in 3D. And it's quite amazing because then you have a non-invasive way to see the retina. And as we saw in the previous slide, retina is also a good way to see what is happening with your body. So we can see from the eyes what is happening internally in your body. And then the question is how we can use technology as a way to improve ophthalmological clinical practice. And this is not something that is new for, I think, many of us right here. Like we can use artificial intelligence plus any kind of ophthalmological data that we have. Let's say in this case, I will be focusing on fundus photos that are images that look like this. Basically, it's an image of the fundus of your retina. Uh, And basically, with these images, you can use it for screening programs. A lot of people is using this for screening problems. So you can use this for automatic detection. You can use it to improve clinical decision making, improve the clinical trials, and discover new patterns. And of course, with AI, as we can do in other fields like X-ray, we can also see things that usually the ophthalmologist will not be able to see. Like we have seen some papers, for example, in X-rays where the AI is able to detect the sex, the race of a certain person. We can do the same thing with ophthalmological images. So, of course, it's never as easy as it looks like. And of course, this also has a lot of problems, and this has problems that the scientific community should tackle. If we see usually the pipeline in the ophthalmological life cycle, everything starts with the data. I will, right now, I will not be focusing in any other of the other things. We, of course, with the data sets that I will show you, we created models, we have a lot of papers, but my idea will be just focusing on the data because I think it's the most important resource for most of you right now. And it's the most important one because if you don't have data, you cannot do any of the other things. And if your data is really low quality or it has certain problems, those problems will be propagated to all the other steps in the machine learning deployment and development process. So we know that having good quality data is really important. And also we know that having a good representation of the data is also important. So if we think in the places where we can use AI, like ophthalmological images plus AI, and where these technologies will impact the most are usually the LMICs, right? Like are the places where you don't have a lot of ophthalmologists. We have the case of Uganda, for example. We are doing a project in Uganda And in that case, they have three ophthalmologists in the whole country. So those are the cases where you actually need more tools to support these people. So this is a plot that I really like. That is a plot that relates the number of ophthalmologists with the GDP of every country. And you can clearly see that, of course, if you have a higher GDP, so basically your country is richer, also you will have a more ophthalmologist. So citing a colleague, there may be just more Ethiopian ophthalmologists in Chicago than in Ethiopia. Basically because these people tends to move to also high income countries. There is also a problem with the data distribution. And I mean, I didn't say that, but I'm from Colombia, South America, and my colleague Luis Felipe Nakayama, even though his last name is not really Brazilian, he's Brazilian, he's also from South America. So we are from countries that are basically underrepresented. Um, And if we see where most of the data sets come in the case of retina, most of them will be coming from the United States and China. And I think this is common in all the medical data sets. It's not only for retina, but this plot is just retina. And also you have some representation in Europe, but then other regions like Africa, South America are usually not well represented. Uh, this lack of representation will also make that the models that you train, the models that you use, are basically not learning the representations of specific patients in these specific regions. Then other thing, and something that I really hate because I work with fairness and bias, uh, are the cases where you have a data set where they only have like clinical labels. And this is, I think, really common, right? Like you have a data set and they share images and the disease. That's it. That's really hard for fairness and bias because usually you need a subgroup to do the analysis. You usually need some social demographic features so you can understand what is happening behind just the clinical task because maybe the model is just overfitting to the majority class, like white people, for example. And this is something that happens a lot with ophthalmological data sets. So if you see most of the most popular ophthalmological data sets that people are using, basically they just have the images and the labels. There are no demographic features. And there is a lack of clarity in the way how they collect the data, the way how they level the data, and the data quality assessments. And this is something that you can see here. Like if you see most of them data sets are not sharing any social demographic features. Some of them are sharing age and sex, but other features are really hard. And in order to tackle this problem, uh, we developed the Brazilian Ophthalmological Dataset, BRSET. The idea of BRSET is this is a ophthalmological dataset of retina fundus photos from Brazil. So these are Latin American patients um, from three ophthalmological clinical centers in Sao Paulo. This is a real world data set that I created with retina specialist. It has multi-labels and multiple quality assessment, really similar to how they do it in clinical practice. This data set contains more than 16,000 images from more than 8,000 patients. And uh, so basically, everything, all these things that you can see here were defined and designed in the Laboratory for Computational Physiology at MIT. I met my colleague there. And if you know the philosophy of this laboratory with datasets like Mimic or platforms like Physionet, usually the philosophy is let's try to have open data because that's the way to push research. Otherwise, it's really hard if you're just keeping the data for your own institution and you're just having results by yourself. It's impossible to do what a community can do just by yourself. So this data set and all the data sets that I will show you today are publicly available. You can just go to Physionet, you can just register and download the data. Uh, just to tell you some things about this Brazilian data set, BRSET. They were created by retina specialist labeling. We have demographic features. In the case of BRSET, we have sex, age, comorbidities, diabetes time. We also have anatomical features, macula, vessels, optic disc. We have a quality parameters that this is usually something that sometimes lack in this kind of data sets, like they share the images, but then you go and see the images and many of them are completely black. Like it's really common to see just black pixels in the whole image. So we are also sharing quality parameters. For every image, we have parameters like focus, illumination, image field, artifacts. So we make sure that if you want, you can filter for by the images with the higher quality. Also, if you want to do an analysis of the quality of images and see how that is impacting the final model performance, you can also do it. Um, and we also have 12 possible pathological labels. I'm not showing those right here because it would be a huge table, a huge list, but you can check those in the paper. And of course, as I mentioned, we try to make sure that everything is publicly available. So the data set is available on Physionet. You just go to Physionet, register. The name is BRSET. As most of the medical data sets in Physionet, in order to access to the data set, you should do a credentialing course. Even though the course is completely free, you should be able to do the course for free and get access. It's just something that we do to make sure that people will use the data correctly, and it's more like for ethics. But the course should be free, and so once you do the course, you just put the certificate there, and you should be able to download the images. So it's just the protection that we do for to make sure that people is using the images correctly. And then also, if you want to check the code, because again, my focus here is not showing machine learning models or deep learning models. You can check the paper if you want to see the kind of tasks that we can do. I can tell you this model works for diabetic retinopathy and the classical retina diseases, and also for some sociodemographic prediction, like you can predict sex or age from the images. I'm not showing the models right now. But if you want to check the code, if you want to try to run the models, to replicate what we did in the paper, you can just go to the GitHub and all the information is there. So this for one side. But then we discovered that retinal images were a nice solution if you are in a place where you have a tabletop camera, which is not always the case. And this happened to us when we started thinking into, let's say, in Latin America, in the bigger hospitals, yeah, we have a lot of resources and you can get any type of imaging that you want. But if you go to rural areas, it's a different thing. Because in rural areas, and I'm pretty sure that also happens here in Europe, like if you go to certain specific rural area, you will not have a lot of resources and they will have like a small clinic. So in those cases, maybe it's harder to have a tabletop camera. What are the difference between a tabletop camera and the other option that is a mobile or handheld camera? Basically, you can see here the difference. Like the image in the right is a tabletop camera. It's like a huge device. Of course, is more expensive than a mobile camera that is just some device that you adapt into a phone. So you can actually take just some Samsung, adapt the camera, and then you have a portable device so you can take from those photos. The first one, the tabletop, is more expensive, of course, but also will give you high resolution images, is more stable. Uh, but of course, it also requires other things that you need. You should move to the place where you have the camera. They need a specialist, like a technician, to take and calibrate the camera correctly. So this is also harder to use and more expensive. But then for the other option, that are the mobile cameras, these are portable, flexible. So if you have a patient with a certain problem and for some reason the patient cannot go to the hospital, this is a good solution. You can just take the camera there to wherever the patient is. Um, the costs are lower. So basically, this is a cheaper solution. So if you're in a hospital where you don't have a lot of resources, you can get access to a mobile camera. The image quality is a bit worse than the tabletop camera, but it's still something that you can use. And it's mainly a good solution for LMICs. So this is our second data set. This was our second approach using or creating a mobile Brazilian ophthalmological data set. And this is a data set, and this is a modality that basically is not out there. This is the first large-scale mobile ophthalmological data set. Not in Brazil, not in South America, in the world. Um, it was created by a diabetes campaign in Brazil. It contains 5,164 images from 1,291 patients. And again, this is also publicly available. And something that we are kind of proud to say is that in this second data set, we managed to increase the number of demographic features or population variables. So in this case, we also have other quite interesting sociodemographic features like educational level, health insurance, and other lifestyle conditions like smoking, alcohol, obesity, that you can use also to understand a bit more the fairness and bias in this data set. Again, as in the other one, we also have image features, and we also have some clinical labels like diabetic retinopathy and macular edema. And this one is also publicly available. The paper, the data set, the codes are all there. The code you will see if you check the repo is really similar to the BRSET repo. And finally, one last question is, right now we have been working a lot with images, but what about text and what about large language models for ophthalmology? Because this is also something that people is using, and this is also something that will impact LMICs. The way how you can use a model like some ChatGPT in your country, maybe for education, maybe to help to support diagnosis, is also something important. So in order to do that, we created this last multimodal ophthalmological question answering data set. Basically, we started with a cohort of original questions from the certification exam in Brazil. We translated with native ophthalmologists in different countries. We translated to Spanish, English, Filipino, Mandarin, Chinese, Hindi, and French, making sure that the questions are also relevant in the other language. So the question in Brazilian Portuguese for the Brazilian population and Brazilian context, when you translate to Filipino, for example, is also relevant for the Filipino population, is also accurate for the Filipino population. In this case, the ophthalmologist did this translation, made sure that this was like this. And that way we end up with a multilingual ophthalmological data set with many specific categories inside of the ophthalmological field that I will not mention right now because it's a huge, you can check the plot. Everything is in the paper. And we evaluated this data set. This was for AAAI last year. So you can see that the models are maybe not the state of the art right now, but with models like GPT-4, GPT 3.5, Llama 3 of 70 billion parameters, Llama 2, Mixtral, and Queen. I will not tell you go and look at the table because I have this plot right here that you can easily see and understand what is happening. Basically, if you see the blue bar is English. And usually, in all the cases, I mean, other languages like Spanish and Portuguese maybe are well represented in the internet, and then they are also well represented for GPT. But other underrepresented languages like Mandarin, Filipino, Hindi are not well represented, and the performance is usually decreasing a lot. So this is indicating that basically, depending on the language and your social conditions, maybe yes, the answer that you will get from ChatGPT, for example, will have a worse quality than what you expect in English, increasing the gap between rich and poor countries. Again, this is everything is publicly available. You have the data set, you have the paper. Here you have the links and also the code. So you can replicate everything that we did. That should be it. And now here you have all the links, and I'm open to questions right now.